Morning, y'all. Adrian, you must like your morning coffee. That thing was like a gallon, wasn't it?
That was my water.
Nice.
Yeah,
They sure make some awesome thermoses now. I
I
love them.
know. Those were the battles at Marshalls. Got it all the Christmas white elephant gift.
Oh, cool.
Yeah.
That's not white. White elephants are like leg lamps and stuff like that.
It does work good for coffee though too.
All right, my friends. Today we touch infinity. We shall touch infinity. Let's see. What are we going to do first? Shall we do? I am getting us a screen to look at. I think we'll start with the programming of the calculator to add lots of rectangles for us. That was glorious. Okay. So what I want you to understand from the program I'm writing is not so much, and actually, if you have your graphing calculator, I'd kind of like you to write this along with me. So warm up your fingers. But it's not so much to have the program because I could just send it to you. It's more that you understand the logic of what the program is doing because I think that teaches you some things. And so you don't have to have any prior programming experience to understand this. Maybe you've never programmed anything in your graphing calculator before, but fortunately, basic language is, well, as it's defined, basic. And so you'll totally understand the logic of this. And so let's just consider for a second the problem involving summation. Let's see, I don't think I want to write it that way yet. Let's just consider the function, let's keep it simple, x squared plus 3, and that's find the area between 1 and 4. And let's choose, notice the distance between those is 3. Let's see. 12. Let's choose 24 rectangles. And I think you would agree that that's not good. Like that's way too many to kind of do by hand. But what I want to do is kind of just start writing out, and you already know this, well, at least I hope you do, but I'm just deepening your understanding of it. So we're starting at 1. And then the last thing we have to decide is, are we going to do this as a left or a right hand? And so maybe we'll do both, or at least start writing them out down. So let's do left to start with. Switch colors. So what does left look like? Well, first we got to establish what our width is. And so let's go back and establish our width. And let's see, our width is always found, the width of our rectangles is always found by seeing out how far are we going. Oh, we're going from 1 to 4. We have a distance of 3 to work with. That's how wide our shape is that we're finding the area of. But then we decided to divide it into 24 rectangles. So that's 3 over 24, which is an eighth or 0.125. So that's a really skinny rectangle. So that means, oh, this is a pretty decent approximation, you should say, because that's pretty thin for a rectangle. So, okay, cool. So what does that mean? Well, our area then would be found by taking that width and multiplying it by each of the heights. And so because this is a left-hander, I don't think I'll even draw a picture of it this time. Let's see, the first one would be when we stick in, what are we sticking in for X to get our first height?
0.
Not 0, because we're starting where?
Wouldn't it be 1?
Sorry, 1. I meant 1. I meant at the beginning.
Yeah, at the beginning. Good job. Where would we be starting if we were doing a right hand? What would our first Y coordinate, what would the X be that we'd plug in?
1 plus our.
Yeah, 1 plus our width. So it'd be 1 1/8. Does that make sense? And it'd even be worse if we did a middle, because it'd be 1 1/2 or 1 1/16, right? So are you beginning to picture that okay? So since this is a left, our first one will be f of 1. And so we got to put 1 into our equation, which I'm not even going to do this time. And then what do we do? And I want you to think a little carefully. What do we do then to get our next one?
You add an 1/8.
You add an 1/8. You read my mind. It couldn't be said any better than that. You add an 1/8. And of course I can do that in my head. So I want to write 1 1/8. But what do you do to get the next one?
You add another 1/8 from the previous number.
Yeah, you just add another 1/8. And I'm going to write that a little differently this time and just say 1 plus, well, 2 of those 1/8. Again, you would do that in your head, right? I mean, you'd probably add that in your head and say, oh, that's 1 1/4, and you just kind of do it, right? But I want you to think today, because we're going to ask a computer to do this. So you sort of, in a sense, add 1 plus no 1/8. And this is 1 plus 1/8. And then 1 plus 2/8, and so on and so forth. And so I'm going to say f of 1 plus 3/8. And then I'm going to say dot plus dot dot dot. And how do we know when we're done? Think really carefully about this. How do we know when to stop? Because remember, we're going to have a computer do this for us. How do we know when to quit?
When we're an 1/8 away from 4.
Is
Or
he
just
right
when-
about that? When we're an 1/8 away from 4? And if you have a different idea, say it. You don't have to necessarily comment on what Eve said.
I would have probably said when that little number that we're multiplying the 1/8 by gets to 4, or to, I mean,
Yeah,
to
in other words-
24.
In other words, Felix is looking at that number right there, right? Like, how do we?
I'm just thinking, because that would probably, I mean, this is probably getting ahead of where we're at now, but that would probably be the easiest thing to think about if we're doing the program.
If we're starting at 0, though, wouldn't it be till it gets to 23?
I agree with Felix. I think we just said it differently, because if we do 24, then we're essentially adding up all our 24 widths. And if we were to start at 1 1/8, which would be starting on the right, then we'd still add 24 to make sure we get to 4, I think.
I think Justin or someone said something about it wouldn't go all the way to 24 because we're counting from 0, but yeah, same.
Yeah, you're all saying some good things, and I'm just trying to give you some think time and let you reason. But of course, what I really need, I'm going to erase this, but I really just need 24 numbers there, right? I need 24 of them, and that's a lot. But again, we're trying to get a computer to know when to stop, so I don't want to have to count them up. And of course, if there's 24 of them, that's a lot to count, and you can kind of even lose track counting by hand. The fact that we're in a sense starting with 0 of these, what a few of you commented on is the fact that that last number right there is indeed, I'm going to erase this too, but that last number right there is going to be 23, because if we have a 23 there, then since we started at 0, that would actually be 24 numbers. Does that make sense? So we are stopping 1 short. And so what Eve said at the beginning is also true. We're going to stop an 1/8 short of 4, because 4 is our right-hand endpoint. We can't get to 4. Otherwise, we're outside of our range, because it was a left-hand endpoint. And so So in this case, because it's a left-hand endpoint, if we go from 0 to 23, then we're great. But if we stick 24 in there, then we've kind of went too far, if you will. So I don't know how much that makes sense. But if you understand the logic of that's what you're doing here, and the point is, because you have 24 of them, you got to be a little more systematic about this, right? You got to be a little more careful. And you could do this by hand if you needed to. But what I'd like to do now is just switch the logic and see if we can, well, get a computer to do that. Computers are really good at, can you see that if this number here is first a 0, and then it's a 1, and then it's a 2, and then it's a 3, computers can do that. And really what we need to do is just add all of those things up. And again, we save some trouble, because really to make it a rectangle, 1/8 should be with every one of these, right? It's 1/8 times f of 1 plus 1/8 times f of 1 1/8 plus 1/8 times f of 1 1/4. But let's just put it out front and save it for later. So that's just out of convenience for us, right? So all I got to do is just carry that out, know when to stop, and I'm going to get the right answer to this, right? And so this is embarrassingly simple. I'm just adding up. I'm adding and multiplying. Can you add and multiply? Can you plug numbers into the equation x squared plus 3? Then you can actually find an approximation for the area of this curve. All right. Stop sharing. Unfortunately, I can't show you both of those at the same time. So I'm going to switch to the calculator now. Let's see if we can write a Riemann sum formula that'll do this automatically. And of course, what's awesome about the computer is, or even a simple calculator like this, is we don't have to pick 24. We could pick 50. Remember, the larger we pick n, the more rectangles we pick, the narrower each of them gets, then the more accurate our answer gets. So interrupt. I'm going to try to go slow enough that you can keep up, but you might get a little bit behind. I don't want to go slow enough that every single person has this in their calculator. We can talk after class if yours isn't quite working, or something's missing. We can have after class. We'll fix it if you care to have this in there. But remember, this is obsolete. We're not going to do this for the rest of the class. You don't really need this. And I'm showing you this because I want you to understand the logic. Okay, so here, notice this is called y1. This is like your first equation, and then there's y2 and y3 and y4, and I'll show you why I'm pointing that out in a second. But we said, okay, we're going to make the equation x squared plus 3, and we want to find the area of that curve. And just for the fun of it, I want to graph it really quick and look at it and go, oh yeah, parabola. Okay, great. And now we're going to go to program, or we're going to write our program. And this virtual one, I've never written a program in here before. And if you've never been in here before, that's what you're going to see too. So you can execute a program. I don't have any, so I can't execute it. I can edit one. I don't have any, so I can't edit them, but I can do a new one. So create new. And it's giving us the option. And notice the cursor is blinking with an A for me anyway. Because when I hit these, notice that, well, let's pick the 7. Notice there's an O up there, and the 8, there's a P up there. Right now it's blinking with an A. So I'm going to actually get the ability to give this thing a name. So I'm going to type Riemann. And I should even probably say, I think I will actually. I'm going to say L Riemann, because this isn't going to, right now we're just working on something to the left. So this is L Riemann. RIEMANN. I don't know if I said this in the syllabus. I think I did, but I'll give random extra credits that occur to me either in my head or because you ask me a question and I choose not to answer it immediately, or maybe I don't know the answer. And then I give it to you as an extra credit. Well, here's my first extra credit. You go research quickly on Google, Riemann, who's that? Most likely it's a dude. It's a person, a woman, a man, I don't know. A famous mathematician that either put a bunch of thought into this, or maybe died, and the Riemann sum, which is what we're studying here, is named after him. I don't know. And actually, embarrassingly, I don't know. Go investigate it. That's kind of worth figuring out. Who is this person? Now, what we want to do is let the person using this decide, do you want to find the area from 1 to 4? Like that's a decision that can be made. So we'll call that A and B. The A is 1 and B is 4. So I'm going to use a command here called prompt. And now that I'm in this program, most of the things that we need are actually behind the program button. So if I hit program and then arrow over to IO, there is a command there called prompt. And you can't just type PROMPT. It thinks you're multiplying 7 numbers if you do that, or 6 numbers. This is a command. So I'm going to prompt the person for, and notice the cursor is not blinking with an A. So I got to hit alpha, the green button, to get A. I want to prompt for A, comma, and prompt for B. So there's my 1 and my 4. And then the other thing I want to prompt for is how many rectangles, because that doesn't have to be 24. Like, why not let them choose? So I'm going to keep going and say prompt for N. We've been using N, so let's keep using N. Lovely. So now the person would have typed in 1, 4, and 24. Now, what is it I want to do with those things? Well, what's the first thing we did a second ago? We figured out the width of the rectangle. So I'm going to take B, this was our formula, right? I'm going to take B minus A and divide that by N. Who can tell me why that's not going to work?
Because the division happens first.
Division happens first. What do I do to fix it? You've seen this mistake lots of times, I hope. So I'm going to go back here
You
and
need to have parentheses.
yeah, second insert parenthesis, back. Second insert, put another parenthesis. Now it'll work. Now what I want to do is call that the width. And so you don't say equals in this language. You go over here to store, STO, stow it in W. So now I have 1/8 figured out. Does that make sense from a previous example? I now have 1/8 figured out. I know the width is 1/8, and I need to know that because that's what I was adding each time, right? To the X that I was plugging in. Oh, we're doing great. I'm loving this. Okay, so now I'm going to have now I want to like keep track of all these numbers I'm adding up. And so I'm going to pick the letter S for sum, but if you've used your calculator before, you might have stored a number in S. In other words, right now, S might be equal to 19 or something. So I'm going to take 0 and store it in S just to reset the letter S and make sure there's no numbers stored in it. So I'm all set to start adding. I'm all set to start adding my rectangles together. I'm going to store them in the letter S, and that's going to be my warehouse. Now I'm going to do something that won't make sense till a minute from now, but I'm going to go back to program, and let's see, where is this one? I don't remember. I think it's control. So if I go down control, notice the if command. We're going to need that in just a minute. There's label, LBL, label. I'm going to label this, doesn't matter what I label it. I'm going to label it L. So in basic command, what I just did is that's line, what is that? 1, 2, 3, 4. That's the 4th line of the program. So I can't call it 4, unfortunately. This is too simple of a program. So I'm sort of labeling that line K. This is location K, and you'll see, or I'm sorry, L, and you'll see why in just a second. Just ignore that for now. Okay, I'm all ready to start. Let's start adding stuff up. Now what I want to do is do the adding that we just did a minute ago. So didn't we do this? Didn't we take, because we started at 1, didn't we take 1 and put it into the equation to see what our Y value was? F of 1, wasn't that the first thing we had a minute ago? So I'm going to do that now. Except for where is this equation stored? Well, it's not in F of X, it's in Y1 of X, right back on our other screen. So if I remember right, I have to go to variables to find Y1, variables, let's see, Y variables, yeah, function. And there's Y1. So I want to take Y1 and I want to evaluate it. What do I want to evaluate it at? Again, this is like F of 1, but what do I want to, I can't say 1 here. What do I want to say? I can't say that.
A.
Yeah, it's A. Wasn't A where we started? So So that'll give me my first answer. And does it make sense why this is left hand? Because you can't stick A in if this is a right hand. So this is now I have my first height. So what I'm going to do then is say, okay, cool. Add that to the sum. Add that to S. So since S was saved to be 0, I've sort of taken my first height, I've added it up, and then what I'm going to do is restore that in S. Again, I'd like you to, what I'm interested in teaching here is the logic, not the program. So I'd like you to interrupt because I'm trying to go slow enough that you understand the logic. So what I'm doing is this is going to be my counter. And so now S is now the first height. And so great, I've got my first height. But now I need to add my second height. How am I going to get my second height? How do I get my second height? Well, the first thing I got to do is move to the next number, right? I got to take A and I've got to add something to it, right?
Is it Y1A plus N?
Well, I don't even have to do Y1 yet. I can just take A and, well, in the language of our example, I was adding an eighth to it, right? Making it an eighth bigger. But remember, it's not always going to be in an eighth. So what should I be adding to it?
W.
Nice job. W.
N.
Let's see. Yeah, and the cool thing here is that notice I'm adding W to it and I'm done. I can just restore that back in A again. Now there's better ways to do this. For those of you computer programmers, there's like a for next loop, if that sounds familiar to you. And actually I've used it a hair, but I couldn't actually teach it. But I'm going to do this even the simple way. Aren't you just adding an eighth every time? Every time you get an answer, you just add an eighth to it. And then you plug it in, get a Y value, add an eighth to it, plug it in, get a Y value. And so now that I've done this, now my X's went from 1 to 1 1/8. And so here's.
Shouldn't that be A times W? Or am I mistaken?
No, not A times W. It is literally, so our A was 1 and our W is an eighth. And so if I add 1 plus an eighth, I get 1 1/8. And so my new kind of X value now is 1 1/8.
Okay, we're doing that like at the end. Or...
Oh, gotcha. Yeah, the times eight. Good job. I see what you're saying. Yeah, and I could say times an eighth now and sort of add rectangles, but I'm just going to add the heights and I'll multiply by an eighth at an end. Thank you for saying that. And so I'm all set now. All I have to do now is go back up and rerun this statement right here. But I got to first make sure I haven't got too many of them, right? Remember, I got to stop at 24 of them. And so here's the way here's the way you test that. So if I go back to the program button, there's this thing called an if. So if A is, and notice right above math, it says test and it's in blue. So I'm going to say second test less than. As long as A is less than B, remember A for us was 1 and B was 4. So A is going from 1 to 1 1/8 to 1 1/4 to 1 3/8 to 1 1/2. And so as long as A is less than B, then keep going. And notice this is going to keep it from getting too high. In other words, it's going to stop kind of where, who said that? I think it was Eve. Where Eve said, this is going to make sure it stops before it actually gets to 4. Does it make sense? A will never be 4 here. At some point, A is going to make it to 4 and it's going to say, is 4 less than 4? And it's going to say, oh, no, it's not. And then it's going to stop. So if A is less than B, then I actually want you, go ahead.
Where did you get the less than symbol from? I'm getting kind of a lag on my video feed. I
Right
apologize.
above math, it says test. So if you say second test, then that's one of your options.
Thank you.
As long as A is still smaller than B, then go ahead and redo this. And this is where label L comes in. So now I say, if this statement is true, then I'm going to hit program and go over to, I'm at control right now, and down at the bottom, there's a command called go to right next to label. I'm going to go to line L, and that's why I labeled it line L. So this is saying as long as A is still, as long as my 1 and something, as I'm adding 1/8 to 1, as long as that's less than 4, then go back to L and notice what it's going to do then. It's going to say, okay, well now plug in your new A. Remember your new A was updated to 1 1/8, plug that in. You get a new height and add that to the old S and then restore it in S again. And so now you've just added another number to your first height. And then increase A by 1/8. As long as it's not too big, go back and do it again. This is called an iterative loop. It's just going to keep doing that until finally A is not less than B, in which case it will skip the step that says go to L. So an if statement is, if this is true, then go ahead and do this line. If it's not true, then skip to this last line. And we're done now. All I have to do is write the answer down. So I go to program, and under IO for input output, there's display. And at this point, S is now equal to the sum of all of those heights. And so if I take that S value, and as I think Felix said, I multiply it by my width, which was W, then I've got the answer. I'm done. Do you see the logic in that?
Really quick, how
Yes.
did you get Y1 in there?
Y1 is found by going to variables right here,
Okay.
variables, and then you have all these choices that involve statistics, but right to the right of the variables, it says Y variables. If you go over there, and then there's all kinds of variables, function.
Thank you.
Yep.
So I'm
It's-
trying to, oh, sorry, go ahead.
Yeah, I'm going to give you a second to ask a few questions now. I'm sure there's things that you missed, so keep going.
Well,
Go ahead,
it's-
Connor.
It's, I'm wondering, because we put S as 0, and then we did Y1A plus 0 equals, that should be, what is new S now?
Yeah, so let's say that first height was like 2.2. So it's going to say, okay, 2.2 plus 0 is 2.2. So store that. So now S became 2.2. And then it goes down here and updates our A value to make it bigger. And then it goes back to the top, and then it plugs that in and gets a new value. And so it's the new value might be 2.3. And so it's going to say, oh, 2.3 plus 2.2 is 4.5. And now S is 4.5. And so we never went back to 0 again. So it's not going to write 0 over the top of it. That's why I called this line L. It never goes back up there again. See the logic in that?
I think that's the most confusing part for me in this whole thing.
Yeah, this is really neat. It's very reminiscent of my C++ programming.
Yeah. Well, and I'm a computer idiot. Like I can do this one because I understand the logic of it. But more advanced programs are involve more complicated sequences and so forth, and they have more complicated commands, and they have routines already built in. So they don't have to, more complicated programs, you don't have to write stuff like this. There's already a routine, like a for next loop, I think is one of those. So I like this just because of the logic, and that's the reason I'm sort of taking the time to show it to you, because I think it's kind of cool.
Yeah, well,
Go ahead.
that's the thing about this too, is like there's already a whole bunch of programming already built into this to make you able.
Yeah. Okay, so let's test this out. Again, we'll have time after class to troubleshoot this if you want to. But notice right now, what is my calculator doing? Well, it's in program mode, and so this is very important. You got to say quit. So second quit, and when you do that, your calculator is back again. You can go 2 plus 2 is 5 is 4 now, and use it like a normal calculator. But what I want to do now is go back to program, except this time I actually have a program there, and I can say, oh, I screwed it up. I'm going to edit it, or I can make a new one, or what I'm going to do, execute. I want to run this baby. And I would have to hit the up and down arrow keys here if I had like 3 or 4 programs, like quadratic formula. Maybe some of you have that in your computer, but it's already highlighted at 1. And so notice what it does. It says program left Riemann, and then I say enter, and it says, okay, you said, remember it said prompt A, B, and C. So I say, okay, my left value is 1, B, my right value is 4, and we had 24 rectangles. And notice, watch this, think. How long did I have to think? Maybe 1 second. And it says the area under that curve is 29.07. Now, I'm not sure this is working right yet. How can I check if this is working right? Go ahead.
How did you
Caesar.
save the program?
Say again? Oh, how did I save it? You don't have to save it. You don't even have to say save. It's just there.
You could set W to be something different and kind of predict where the area should go based on how many triangles.
Say that one more time, a little louder, Logan. You're
You can set the width of the rectangles to be something different and try to predict where the area should go.
something's wrong with your mic or my hearing. Can other people hear that? Sounds
Seems kind of messed up for me too.
sounds kind of garbled for some reason. Play around with it, Logan, and try it again. Well, what I showed you yesterday, remember yesterday when I said second calculate, and I showed you, and this is one of the symbols we're going to learn today, that little S symbol right there. We said this was going to give us the perfect answer. So if I say, let's fire that thing up. And so our lower limit is 1, our upper limit is 4. And notice it doesn't ask for rectangles because it's choosing billions of rectangles. And so notice it says the answer is 30. So I can trust that because I didn't make it. So, and that should bother you. 30, like exactly 30? You're kidding me. So does our answer make sense then?
Yes.
It does, because the left-hand endpoint is missing, and this might have been what you were saying, Logan. The left-hand endpoint is missing those little triangles at the top. So our answer is going to be too low since this was an upward curve. What can I do to improve my Riemann sum answer if I'm using my little program here?
More rectangles.
Oh, I love brevity. More rectangles. Let's do 100 rectangles.
What was the original equation? It was x squared
X
plus.
squared plus 3. Notice how long it's taking.
Yeah, I was actually just gonna say, like, it did it like way faster with the fact with billions of rectangles, even than like our 24 rectangles. So clearly there's like a simpler way of doing this.
Exactly right. And that's where, this process would cross into computer programming, because it literally is adding 100 rectangles here, and that's very time consuming. And so you can actually start to see the calculator even slowing down. And so notice it's creeping its way toward 30. We're not surprised by that, are we? Let's do it one more time. Is it stupid to do 1,000 rectangles? Well, you saw how long it took to do 100 a second ago, right? Well, isn't this going to take 10 times as long? I think it took about 3 seconds, maybe 4. Well, now it's going to take 40. It's going to take a long time. So you can't just type in 999,000. Like, you got to start becoming a computer programmer. But 1,000 rectangles is no joke. And the fact that it's doing it in less than a minute, I'm guessing at that. The fact that it's doing it in less than a minute is pretty sweet. I mean, this is amazing. But notice, although it's kind of fun to write something like this to do your work for you, it's like I can go make a sandwich now while it's doing its job. You understand it. Like, this is blue collar. Like, it is adding rectangles together. It's just adding them. And the point is, you don't need calculus as long as you have lots of rectangles. And wasn't that true last term too? Did you actually need calculus to find the slope at a point on a curve? No, just find another point that's ridiculously close to the previous point, and you'll get a pretty darn good slope. Well, didn't we just get a pretty darn good answer there to the area under that curve? Is it correct? No. Will it ever be correct? Very important.
Especially since we probably, if we were in real life, might have just been like, it looks like it's probably 30,
Yeah, and notice in this case, because the answer was a nice recognizable whole number like 30, then in this case, I think you could say, hey, it looks like it's on its way to 30. But what if the right answer was, 31.27896? So in this case, I think we might be able to get away with kind of guessing but again, isn't this the concept of what calculus is about? It's a limit. We're saying it looks like as the number of rectangles goes to infinity, this is reaching a limit of 30. But will we be able to ever get 30 ourselves? Answer.
I bet that the calculator would probably just run out of like digits that it can use and give you 30, but not like you're not supposed to. I mean,
yeah. And again, this is the difference between a mathematician and say an engineer. An engineer says, hey, that's pretty close to 30. It's 29.98. Let's go build the bridge. Close enough. It's only 200ths off. That's pretty much the area. A mathematician says, is driven crazy, if you will, by the thought that this will never be right. You could have a billion rectangles and it's still too small. It's always going to be too small. You'll never get it right. So the question of calculus is a limit. You can't ever get the right answer by adding rectangles. Do you understand that? I don't care how many rectangles you have, trillions, a trillion rectangles, you're still too small, theoretically, right? Practically with 1,000 rectangles, close enough. But can you ever actually get there? And that's what I want to take a look at now. I'm resharing my other screen, so. So I've been talking about the same thing now for 2.5 days. Is it soaking into you what's going on? I mean, that in a sense, that's what I want you to leave with, because we're about to try to actually touch infinity. So now it's going a different direction. And this is where smoke will start coming out of your brain. And again, as I've already been telling you, as we're about to go into some deep waters here and start to suffer, remember there's a shortcut here that's going to make this pain obsolete. This is the exact equivalent of, as I think Justin reminded us yesterday, when we use the definition of a limit, f of x plus h minus f of x over h, and we let h go to 0, and we had to multiply the whole thing out. And miraculously, we're able to actually get the perfect slope, the exact slope when h, the distance between the 2 points, went to 0, and it actually did work. But that only worked for us for super simple questions. And that's the same thing here. I'm going to show you how to, the long way, actually get the answer to this right. But it's really painful. And so we're going to work towards shortcuts really quickly, but it's just beautiful to see. And you don't want to miss this. So let's start with a simpler example, just because you'll suffer less if I start with a simpler example. Let's say the equation is not x squared plus 3, but it's only x plus 3. And I want you to think about this for a minute, because you have some problems like this. And let's go from, I don't know, 2 to 7. But the difference here is we actually want to let n be infinity, not 24, not 100, not 1,000, but infinity. Let me take a second to graph this. I'm just going to draw a rough graph since this is such an easy one. Can we find that area exactly? I'm looking for an answer.
Yes, you could with the trapezoidal formula.
Yeah, notice that particular shape is a shape you recognize, and you have a formula for it. So it's like we don't need to add a bunch of rectangles to get the answer to this right, which is kind of cool, isn't it? And you have some problems in your assignment like that. There's 2 shapes that are created that you actually can handle and sort of don't have to do calculus. One of them is this trapezoid that you see here. So the equation has to be aligned for that to work. And the second one would be a circle. The area of a circle is pi r squared. And so if the equation was a circle or some chunk of a circle, like a quarter of a circle, you could use geometry and actually find its area. Again, this is kind of it's a side trail. It's kind of a waste of time. We're looking for the area under everything. But it's good to at least think about this for a second. Well, do you still know? Let's do this using geometry so that we know the actual correct answer to this. Let's see, maybe you remember this. Well, this height right here is f of 2. So if I put 2 into our equation, 2 plus 3 is 5. So that's a distance of 5. This height is f of 7. If I put 7 into that, I get 10. And so those two distances are 10 and 5. Great. What do I do with 10 and 5 to get the area? Who remembers the formula for the area of a trapezoid?
Isn't it half?
I mean, I would just use a rectangle and a triangle because I'm lazy, but
I wouldn't say that's lazy. It's more because you can reason out yourself, which I think is kind of cool. Do you actually need the trapezoid formula? Maybe you don't remember what it is. So as Felix is pointing out, like, isn't that just a rectangle and
It's 1/2 times a plus b times h.
yeah, what you're really doing with the trapezoid formula is kind of averaging 5 and 10, because it's kind of like the top of the rectangle is 5 and the bottom is 10. It's like, well, I can't use the rectangle formula. Well, you can if you average them. So if you average 5 and 10, which is 7.5, and then you multiply by the height of this, which is 7 minus 2. Unfortunately, coincidentally, it's the same as that other 5. Then this would be 35 plus 2.5, which is 37.5. And notice I said equals. That's the profound statement right here. The area equals 37.5. It's not approximately 37.5. It is 37.5 perfectly. So what I want to see is, can we add rectangles as we've been doing and get the same answer if we let n be infinity? What if you succeeded in getting your calculator program written, you might go back and actually test that out. Stick the equation y1 is x plus 3, go from 2 to 7. You can't choose n to be infinity, but choose n to be, say, 100, and run your program and see if you get something less than 37.5. You'll get 37.2 or 36.9 or something like that. But what we're going to try to do here is different. We're going to try to have infinitely many rectangles. So what would I call this? Maybe maybe I'll just introduce the word right now. Integral. What you're studying right now is integral calculus. What we've been doing in your program was Riemann sums, where you add a finite number of rectangles, 1,000 rectangles, 100 rectangles. An integral is where n is infinity. The number of rectangles is infinite. And that should bother you, because if you have infinitely many rectangles, then how could you ever add them all together? Because you're never done. Not only that, how wide are the rectangles? If n is infinity, how wide are the rectangles?
I mean, they're like infinitely thin.
Yeah, isn't this what we did? We said 2 divided by 7 minus 2 divided by n. So in a sense, it's like the limit of this statement as n from last term goes to infinity. What happens to 5 over n as n goes to infinity? Again, I'm saying what is the limit of it? In other words, n is infinity. What is 5 divided by a giant number? It's not just small, which is what Felix said. It actually is 0. The limit of it is. But that's
Right,
only
because
if
it can
n
only
is infinity. And this is the part that's like,
get so small.
so I hope you're comfortable with the fact that it's at least a tiny number, but the limit of it is actually 0. So this should not work, right? Because if the program a second ago, the last thing we did was multiply by the width, and if we multiplied by 0, then the area would be 0, right? So as I said before, what we really have is a battle of infinity times 0, because we're going to have infinitely many heights to add together here too. Didn't we just have 1,000 heights to add together a minute ago? So we're going to have infinitely many heights, but they're infinitely small. And so that's going to approach a number. It's going to approach, well, 37.5 actually, we found out. And so the question is, can we actually work with it if it's infinity? Well, let's take a stab at this. So I'm going to try to write sigma notation for this. And this is the hard part. In other words, and all sigma notation is writing out what we just did with the calculator a second ago and saying, okay, well, let's see. First, since we went from 2 to 7, the first thing I'm going to do is plug in 2. And I'm just going to progressively fix this. I'm going to show you how to think about it. If I just write it out, you'll think, wow, how did you come up with that? But we first plugged in f of 2, and then we plugged in f of, I want you to think carefully. What's our next number? What do I add to that?
Zero. I don't even know with this because it'd be infinitely small, but
It's really this. I mean, isn't our W 5 over n? And
But isn't that 0?
Yeah, isn't that 0? Like,
oh, we're doing the calculus thing where we pretend we're just use a variable until we get rid of it somehow later.
that's exactly right. And the subtle distinction is, like, if I say 0 right now, then it's just going to be f of 2 plus f of 2 plus f of 2, and it doesn't make any sense. But if I wait till later, and that's exactly what we did with derivatives, we said, well, h is 0, the distance between them is 0, but if you plug it in too soon, it doesn't work. And yet if you wait till later, it does work. And let's see if we can get that to happen here. So then the next one would be f of 2 plus 2 of those 5 over n's, right? And so on and so forth. Isn't that kind of the gist? And then when we're all done, don't we have to multiply this whole thing by our width, which was 5 over n? Isn't that what we have to do? Something like that. Maybe I shouldn't write sigma just yet because I didn't actually do anything. Now let's go back and see if we can, instead of writing all of the individual sums, let's see if we can actually write that out. So let's see, the function itself is actually x plus 3. So my point is this right here would actually be 2 plus 3, and this would be 2 plus 5 over n plus 3, wouldn't it? Because that's what our function is in this case, is x plus 3. So how do I say that? 2 plus, how do I write all of these statements identically? How do I write every one as the same exact statement? Aren't they all 2 plus something plus 3?
W.
And here's where it gets, well, the question is, how many 5 over n's do you have? That's all that we have to really quantify here. Didn't we have 2 of them here? And I didn't write it, but didn't we have 1 of them here? How many did we have here? We had none.
0.
So if I say, let's start at 0, k is 0, and add k 5 over n's to this, do you see that that's actually going to produce what we just wrote above it? So this is mathematicians being lazy. So I guess you could say then that this would be, well, 2 plus 3 can be added. So isn't it 5 plus k times 5 over n? And let me go back and add in the thing that I kind of forgot, which is I still have to have this 5 over n in here. and we're letting k go from 0. And remember, what we don't want to do is stick infinity in too soon. We want to stick n in here. We want to say k is going to go, and this is just how many rectangles do you have? Like a second ago, we had 24 rectangles. So it'd be 0 to 23. This is exactly what we did a second ago. So you could stop at 23. And then this 5 over n doesn't have to be inside. It could be outside. And so ultimately then what we're looking at is what is the limit of that statement as n works its way to infinity? 5 over n, 5 plus k times 5 over n. What is the limit of that
5.
to infinity? That's infinity. Now, as I don't know who said that, Felix, doesn't it look like the answer to that is, well, is it 5? Now, the reason that I think Felix said 5 is if n is infinity, isn't this 0 and that becomes 5? But remember, you're still adding lots of them. In other words, it's 5 plus 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 5. But then when you're all done, you're multiplying by 5 over infinity. So it's actually 5 plus 5 plus 5 plus 5 plus 5. You never get to stop. And then when you're all done, you multiply by 0. You can't plug infinity in yet. Do you see why? It's too soon. This looks like a nonsensical statement, frankly. It looks like it wouldn't go anywhere. And just so you begin to understand what we'll do after this section, this is what we call an integral. You replace the sigma symbol with a summation symbol. That's an integral sign. You replace it. And the 7 and the 2 go here, and the equation goes here, and you put a little dx there. So when you switch to the summation symbol, just like you saw with the cheat button on the calculator, it's now assumed that you have infinitely many rectangles, which is why the calculator gave us 30 a minute ago for that other problem, and why, in this case, we didn't have to use the calculator to know the area under this curve is 37.5. If you have infinitely many rectangles here, then the answer will be 37.5. That's the limit of this. So as soon as we get out of this section, this is what we're going to be doing in this course. Like, what do you do to that statement to get the right answer? That's kind of what this class becomes. But for now, we're staring at this horrific statement right here and trying to make some sense of it.
So basically, instead of doing k times whatever, infinitely, you would just multiply it by the
Multiply by what?
derivative of x. The derivative of x.
No, it's related to derivatives as it turns out, but it isn't a derivative. So we'll tackle this. Well, we'll start tackling it tomorrow. Actually, tomorrow's Thursday. We'll start tackling how to do this via a shortcut tomorrow. But I want to show you that there is a way out of this mess. And again, my guess is that's hurting your head. Like when you stare at that, can you see that that's a brilliant way to write down, well, what our calculator just did? Just keep adding a bunch of stuff. Except we didn't pick n to be 24 yet, or 100 or 1,000. Let's just leave it and say n is large. That's all this statement means right here, is n is really large. And so we've been doing this. The question is, can you stare at that and go, yeah, actually, as crazy as that looks, we've actually been doing this.
Yeah, I wouldn't call it mathematicians being lazy. I'd call it being efficient.
Good job. That's exactly the kind of the positive spin on it. It's like, how do you write this down? How do you conceptualize this without the plus, dot at the end and say you never get to quit? So that's what mathematicians do. And amazingly, there is a way out of this mess. I mean, that's the thing that I think is surprising. So go ahead.
I was just thinking about, because you were saying that somehow like we're dividing by, we're multiplying by 0 at the end or something.
Yeah,
But
because isn't this statement right here on its way to 0?
well, yeah, but if you think about how that 5 in there, because we're adding it every time, then it's also kind of like 5n over like times 5 over n, which, you know,
Yeah.
maybe just cancels.
Well, let's go look at this. First of all, let's do what I showed you yesterday, which is just expand it and see if it's actually kind of working. So there's the 5 over n, and now here's all the junk I'm going to add together. And so the first one is 5 plus no 5 over n's, right? So I'm going to even write that in there. So none of them. The second one is 5 plus 1 5 over n. The third is 5 plus 2 5 over n's. I'll write one more. The fourth, or whatever one we're on, is 5 plus 3 5 over n's. And how far do we go? How far do we go with that?
Ever?
Ever. The dot 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 means you never get to stop. Well, if n is infinity. If n is 1,000, you do get to stop, right? Isn't this is what we just did with our calculator? Again, doesn't it look better now? Like, oh, okay, it looks okay now. The sigma notation thing is kind of hard. But let's try to add this up. Can you actually add this up? Again, we can't stick n as infinity in too soon. Otherwise, you have 0 times, well, if you add a billion 5s, do you see that this is on its way to 0 and this is on its way to infinity right now? So we can't stick n as infinity in right now. So let's just wait. Can we make any progress with this? Well, how many 5s do we have inside there if you just kind of focus on, and I think
N.
might be what Felix was saying. How many of those 5s are there? Felix is right. He said there are n.
Infinite?
So 1 5, 2 5s, 3 5s, 4 5s. You have n 5s. There's all the 5s. So I took care of that. And now you have, since we have 0 5 over n's, I'll just start with this one. 1 5 over n plus 2 5 over n's. Plus 3 5 over n's. And unfortunately, that's not that helpful because that just goes on forever, correct?
Hold on though. Can we maybe I'm wondering if there's a way that we could, like, if we put that into its own sum, that turns into basically 0 like we saw, because that's the part that was like basically turned into 0 from the sum, doesn't it?
Say that again. I didn't follow what you're saying.
Well, this part that you wrote in green here is like the part, if you scroll up a bit, it was like k times, 5 over n or something like that. And that was the part that turned into 0. So if we put this green bit into its own sum, then it would kind of just go away, I feel like, and then we would have the 5n over 5.
Your intuition is right, and I'll show you where we can go with this. There is something we can do with that green stuff. Now the problem is infinity, right? We got infinity of them, and that's the dot 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 is what's killing us here. But again, let's just kind of rewrite what we got. I've got 5 over n out front. I've got 5n right here. And then if every one of these has a 5 over n in it, then couldn't I factor that 5 over n out, and I'm just left with 1 plus 2 plus 3 plus 4 plus that goes on forever?
So could we call that 1, 2, 3, 4 forever k? Is that what we were doing up higher?
No, it's not k. Like, we actually need to answer that. And so here's something that a guy named Gauss figured out. So this is a little side note. As the, I don't know if I want to call it an urban legend. I think it was actually true. Gauss was a famous mathematician, and as all famous mathematicians do, annoyed the snot out of their math teacher by basically being smarter than their teacher in 4th grade. And so to keep Gauss busy while all the other kids are trying to add 2 plus 3, the teacher told Gauss to add up the first, I'm kind of making this up a little bit, but add up the first 100 numbers. You know, what's 1 plus 2 plus 3 all the way to 100? And she thought, awesome, or he thought, that'll keep him busy for a while. And unfortunately, Gauss, being as sharp as he is, came back with the answer ridiculously quickly. Here's how he did it. 1 plus 2 plus 3 plus dot, 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 plus 12 plus 13 plus, and I'll just stop at 14. Let's say he was adding from 1 to 14. What Gauss did is said, I'll take that list and turn it around. What do you get if you add those? Well, notice you get 15 plus 15 plus 15 plus 15 plus 15 plus 15. Let me give you a second to think about that. How can you use that to get to the sum of the first 14 numbers without actually having to do it then? How many 15s do you have to add up?
14?
14 of them. I'm going to write that differently. You have 14 15s, but then didn't you add the whole list twice? So you'd have to cut it in half. Do you agree with that? So that's actually 7 then times 15. That'd be 70 and 35. The answer is 105. So Gauss came up with a way, supposedly, of adding up consecutive numbers, 1 plus 2 plus 3. So what's the formula then? What if this went, well, I guess stare at this for a second. Isn't this the actual number, kind of the n, if you will? So I said add up 1 plus 2 plus 3 plus all the way up to n is 14. Does it make sense that this number then became 1 larger than that? And so if you want to add up the answer is n times n plus 1 over 2. Page 345 in your book, this formula is listed. And you probably have never seen it before, but this means we can actually replace what we've just been doing with a formula. Thank you, Gauss. So I'm going to kind of circle this as a side note. So what does our formula then become? 5 over n times 5n plus 5 over n times n times, oops, got excited, times n plus 1 divided by 2. You agree with that? And don't forget, it's in our head. I didn't write it down, but it's in our head that we want to let n be infinity. We're getting close to a place where we can actually let n be infinity. Let's see what happens if we kind of multiply all this out a little bit. 5 over n times 5n plus 5 over n times, I guess this would be n squared over 2 plus n over 2. You agree with that? So that'd be 5 over n times 5n plus, let's see, if I distribute this 5 in there, then that'd be 5n squared over n times 2. Wouldn't that be 5n over 2? You agree with that? And if I multiplied it by this one, it'd be 5n over 2n, which is just 5 over 2. 2. Let's see. I'm bothered by something right now. and you help me figure this out, because I'm bothered by the fact that we found this area back here to be 37.5. And that's because we went between 2 and 7, right? We went between 2 and 7. So is the 2 and 7, is the 2 and 7 in what we're doing here?
Yeah, they're the lower and the upper like limits, right? Or not limits, but like thresholds of what we're measuring.
Yeah, like the 7 minus 2 is 5. So I'm again, I'm thinking out loud. I'm worried we lost those, or they're someplace and we haven't used them yet. So, but 7 minus 2 is 5, and so isn't that where that 5 came from? I don't know.
That's tough because one of the 5s could be from the height and one could be from the width.
Exactly. So
the formula might
unfortunately,
be wrong.
that's right. I think it is in here, but I'm not sure. I'm still a little worried. Because again, we're sort of saying the answer to this. I'm just sort of feeling like this isn't working, because I'm saying the answer to this is going to be 37.5, and I'm kind of going, really? I'm not seeing it. I'm a little worried about that. So let's see, where are we? Well, again, let's just distribute this. If I distribute this 5 in here, doesn't that become 25? You agree with that? Because it's 25 n over n, isn't that 25? Please interrupt. What do I get for this term? I get 25n over 2n. So isn't that 25 over 2? And this last one, I get 25 over 2n. Something amazing just happened. Do you understand what that is?
You got most of your ends out, so you can plug something in for it.
That's
Well,
exactly
the
what-
n there makes that term, as n goes towards infinity, 25 over 2n kind of just goes to 0.
Nice. Up until this point, we could not let n be infinity. We could not let n be infinity here. Why not? What happens to that statement if n is infinity?
It all becomes 0, right? Because all the ones inside become 0.
This
Or
one,
infinity.
this one,
Because of the
becomes,
outside one. Yeah.
that's 5 over infinity, so it's 0. And the inside one, notice it has 5 times infinity, so it becomes infinity. It's still infinity times 0 right now, until what just happened here. Now, n can actually sort of equal infinity, and as I think Felix said, that means this term goes to 0. And so we literally let n be infinity. If n is infinity, 25 over 2 times infinity is 0. And now we can say the actual area is 25 plus 25 over 2. My goodness, friends, isn't that 37.5? Unbelievable. Now, of course, that was a stupid waste of time here because we already have a geometry formula. But do you understand that works just as well if it's curved, where we don't have a geometry formula? I wonder who the first person was to kind of not give up too soon, if you will. And go ahead and try to write this out, write out that red formula and say, well, what if that does work, and like try to make some progress with it. And at some point they would have got stuck trying to add a bunch of numbers together. I wonder if this formula was discovered before this or after this, I don't know. And lo and behold, all that work, and until this turned red here at the bottom, it was all just a waste of time. It's just rewriting, rearranging the wood pile. It's all going to burn anyway. But magically at the end, oh my gosh, just like in Calc 1, oh my gosh, we can let h, the distance between those 2 points, we can let it be 0, and we're getting the perfect slope. Well, we just got the perfect area. That is the definition of an integral, where n actually is infinity.
There is one thing that does seem a little bit too magical to me, which is that part with Gauss, was it? With the numbers adding up?
Yep. And you're probably saying that because you're thinking, does that still work when n is infinity, right? Because then this is infinity, and then this is infinity plus 1. Something, is that what's bugging you?
Which is still infinity, right?
Right, which is kind of like still infinity. But remember, that's the same thing as, where did I write this? This. What's bothering you is that statement right there. What should bother you maybe still, because remember, when you touch infinity, your head explodes. This is equal to 0. What would not bother you is if I said this is approximately 0, then we're fine. Great, no problem now. 5 over large number, really close to 0, totally get it. But we're saying, nope, in calculus, it actually is 0. But remember, infinity is not a number. It means you don't stop.
Well, not even that so much. Like I've kind of, at this point, kind of learned to look the other way when these confusing infinity things come up. But like, I just don't understand for sure how this works, or like how we're certain that it works, if that makes sense. Like it seems kind of like,
Yeah, in other words, there's
I don't really fully understand that part of it.
Yeah, well, and I'd encourage you to stare at this some more. But there are a lot of levels of questions to this. You're exactly right, Felix. And you are, in a sense, a true mathematical mind, because you're staring at this and saying, I feel like some magic happened there. Like there's some steps that need to be justified. And the more mathematically minded you are, the more that you might, if you stare at this, see that there's some things you feel like you need to justify that that's okay to do. If you're less mathematical and more of an engineer type, then you might be sort of okay with what just happened. So I guess all I'd say for now, Felix, is try to codify where you found what you're bothered by, and I'll see if I can answer it. We'll talk about it after class. Can you appreciate that this is going to be, I mean, that was for a line, right? So if we did this for a curve, it's going to get really terrible. If we did this for a squared equation, it just gets awful. I'm trying to decide what I should do with the last 10 minutes or so of our time. I think we're doing okay. I think I'm going to wade into it. I think I'm going to wade into a squared problem, and let's see if we can make some sense of a squared problem. And we'll finish it tomorrow if we don't have time. So let's try f of x equals, again, I want to keep this really simple. The next simplest equation I can possibly come up with is, well, let's try to do the one, what was it at the start of class? +3? Was that what we did at the start of class? +3? And we said, apparently, that if you go from 4 to 1 on the equation x squared plus 3, that the answer equals 30. Isn't that what we said? Is that right? I don't think I have that in front of me anymore. That was the problem, right? And to belabor the point a little bit, this integral symbol right here is also S for sum, but do you notice the dx? The dx, remember, is, so this means something. This is the width of your triangle. But by definition, when you see dx, that means teeny, infinitesimally small, actually 0. That's on its way to 0. And so when you use this symbol instead of sigma notation, you're saying, I want the right answer. I don't want approximate. I don't want to add 1,000 rectangles. I want to add billions of rectangles. This collectively is the equation, which is really the height. That's the width and the height of your rectangles. And this just means add them all up. And then this 4 and this 1 are the limits. The way mathematicians sometimes say that is they're the limits of integration, which again is totally common sense. And again, isn't that a crazy statement? Again, go show this to somebody that you know and try to get them to listen to you. If you make it more than 60 seconds, you should be in sales. Because that looks terribly confusing. But is it confusing? No, this is adding up rectangles. That's why I spent so much time 2.5 days, making sure you understood the concept here. This is just beautiful because we're saying that the width is essentially 0. Or at least it's on its way to 0. Maybe I should be a little more precise and at least draw an arrow and say it's approaching 0. That's what we're going to be working with all this term, but it's just area under a curve with infinitely many rectangles, infinitely many, infinitely narrow rectangles. Let's see if we can survive what we just did, except with a squared equation. And so we'll get part of the way through this and then we'll pick it up tomorrow. I find writing those sigma notation things really, really confusing. And so let's see if we can picture this a little bit. Let's see. So our width is 4 minus 1 divided by n. So that's 3 over n. So there's our W. Highlight that. That's the width of our rectangles. And so we're going to say, let's see, sigma, we're going to add up. And notice if it's infinity, do you agree that we don't care anymore if it's left hand or right hand or middle? Because there's infinitely many of them, it doesn't even make a difference. So I'm going to stick with the left hand thinking here. And so what did we do? Let's see, we started at 1 in this case. We started at 1 and we added no widths. We added no widths to it, right? And what did we do with that number to get the height? Oh, that's right. We plugged it into this blue equation up here. We plugged it into that. So in this case, we have to take that statement and square it and add 3 to it. Do you agree with that? So is that right? Am I right? Am I done? That's the answer. So let's see, is that working? So this would be, since k starts out at 0, this would be 1 squared plus 3. That's kind of my first height. And then the second one would be 1 plus a width. And I'd be squaring that and then adding 3. So there's kind of my second one. Yeah, I think it's working. Do you agree?
So I'm confused. What is K?
K is kind of the counter that we had in our program. In other words, we start out with our first rectangle and then our second and then our third and then our fourth and our fifth. So K marches from 0 to n by ones. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So really K is like, which rectangle are you on? We're on our 0th rectangle, our first one, and then our
So
second, third,
do we eventually replace K with Gauss's like equation?
That's exactly right. The same thing's going to happen here. So that's going to go away. We're going to end up with 1, 2, 3, 4 again, just like we had a while ago. And so do you understand that this is not infinite? Because n, we haven't let n go to infinity yet. So this is what we've been doing. If I say n is something reasonable, like 5, let's have 5 rectangles or something like that, fine, I can just do this by hand. And I wouldn't even write out this nonsensical, crazy, confusing statement. Because again, when I write sigma, most of you, probably half of you, are staring at this, trying to get your mind around it and trying to be convinced, yeah, that actually is right. That is what we've been doing. So it's only infinite when we let n go to infinity. And so let's see. Oh, and what did I forget? I forgot one thing. What is this right here?
That whole thing's the height, right?
Yeah, aren't those all the heights?
And then you need to multiply it by the width.
Exactly. I forgot the width, didn't I? So that was a mistake. So there, I got it in there. So again, let's try to expand this out. So I'll go ahead and say dot, dot, dot here and write times 3 over n since I forgot it. So let's see, what would it expand out to this time? I have 3 over n, and I have 1 squared plus 3, 1 squared plus 3. And then I'm going to write kind of a giant plus sign, and then 1 plus 3 over n squared plus 3. And then another giant plus sign, 1 plus 2 3 over n's squared plus 3, dot, dot, dot. So there's my first rectangle, there's my second, there's my third. So like last time, notice all these 3's, change colors. There's a 3 in that one, there's a 3 in that one. Every one of them has a 3. So isn't there n of those 3's? So that takes care of the 3's. But then I still have the 1 squared plus 1 plus 3 over n squared plus 1 plus 6 over n squared plus, let's see, what would the next one be? 1 plus, that'd be 3 times 3 over n, 1 plus 9 over n squared, so on. True? I see the time, we're almost done for today. So now I'm going to have to square all of these out. So 1 squared is 1. And then this statement is a little uglier to square out. I have 1 squared plus 1 times 3 over n times 2, which is 6 over n, plus 3 over n squared, which is 9 over n squared. So that's this one, plus 1 plus 12 over n plus 36 over n squared. That's that one. Can I do anything with that? Again, I'm just trying to clean that mess up. Do you notice every one of these terms has a 1 in it? So at least I could do that, right? So I have 3 over n on the outside. I have 3n plus 1n. That takes care of all those ones.
You could take out 3 over n from every single term, right?
No, every term doesn't have 3 over. Let's see. Yeah, okay, I see what you're saying. In other words, you're next. You're looking at this statement next, and you're saying, can I take something out of that?
Well, couldn't you take 3 over n out of 9 n squared too, and through 36 over n squared?
That's a good question. I'm not sure. In other words, you're trying to put them together. But notice you can add fractions with common denominators. So at least I could say this, couldn't I? That if I look at those green ones that have 6, they already have a common denominator. So wouldn't I have 6 plus 12 plus, let's see, what's the next one going to be? 18, yeah, 18 plus, so I'm adding 6 every time. Would you agree that's all of these? And now I'm going to look at these pink ones. And so that it fits, I'm going to write it right here. So there's a 9 and then a 36. What's the pattern there? Let's see, it was a 3 squared is 9, and that's not good. And then a 6 squared is 36, and then a 9 squared is 81, isn't that right? So this is plus 81. So it's 3 squared, 6 squared, 9 squared, 12 squared. Is that right? And both because of time and also because I want to let you think about it from there. Actually, I want to write one more thing down and then I'll shut up. So 3 over n, and then we have 3n plus 1n, which is actually 4n. And then every one of these green ones has a 6 in it. So if I pull the 6 out front, then isn't that actually 1 plus 2 plus 3 plus 4? And what do these pink ones all have in common?
9.
Get a 9, so there's a 9 over n squared I could pull out, and that would leave 1 plus 4 plus 9. So I know how to handle that one thanks to Gauss. I know how to add 1 plus 2 plus 3 plus 4 all the way up to n. But notice this one is actually 1 plus 1 squared plus 2 squared plus 3 squared. I don't know how to handle that one. However, if you look again at your book on page 345, there is a formula there, but I'm going to show you how to get that tomorrow. But oddly, we're going to be able to make progress with this, and we're going to let n be able to let n be infinity, and we're actually going to get exactly 30 if we don't quit. And again, don't forget, like this is only the simplest parabola I could possibly make. What if the equation was sine or e to the x or something insane like that? This could be terrible. And so the fact that there is a shortcut for this is exactly what happened last term. The fact that there's a shortcut that keeps us from having to do this is awesome. But it's kind of cool just to see it a little bit. So, sorry, I went way long. Get out of here and stay after. We're not done as far as I'm concerned. You can stay after and we can keep talking about it a little bit, but I'll pick it up there tomorrow as far as what I show formally.
By the way, I was thinking that if we, when we first finished making the little program thing, that it might eventually just kind of run out of, I guess, decimal places and just round to 30 or something. And so I set it to go to 100,000 rectangles, and it's been doing it the whole time since we finished that, and it just finished, and it's still only like 29.999. So waste of time.
I'm totally glad you did that, and you're exactly right, Felix. If it did say 30, it would be because it rounded it, because you'll never get 30, and because you did 100,000, that's 100 times more rectangles, which means it took 100 times as long. So if mine took 4 minutes, then yours would take 400 minutes. Mine must not have taken 4 minutes, or yours wouldn't be done. But yeah, that's really interesting. So, and that's the beauty of calculus right there, is no matter how many rectangles you add, you never get the answer right. If you're not a mathematician, close enough, it's 30. If you are a mathematician, then you got to do what we're doing right now and actually look at the concept of a limit. This statement that we made right here in black, if we keep working, right now I can't let n be infinity because the whole thing explodes again. I get 0 times infinity still. But if I replace both of those infinite sums, one is the infinite sum of individual numbers, 1, 2, 3, 4, 5. The next one is the sum of squares. If I replace both of those with a formula that adds them up for us automatically and distribute 3 over nn, then I'm actually going to, at some point, be able to put n is infinity in there, and I'm going to get 30, which is unbelievably cool that it could even be done. We're touching infinity. It's amazing. Oh, how's your brain? Is it in pain? Should be.
It actually is pretty cool that we can work with infinity but still get a number in the end. Like you would think if you do all this stuff and like solve it out, then you would just lose your numbers, you know?
Yeah.
Infinity.
The beauty of this is amazing. I mean, there's all kinds of other questions like who cares? Does anybody ever need to know this and so forth? But this is beautiful. I mean, the fact that you can actually play with this, and I mean, mathematicians are crazy folks. The ability to persist with questions like this. And, our next question is, is there some way to add up the sum of squares? We added up the sum of individual numbers, but, Gauss's method of turning the list around doesn't work here. If you take 1 plus 4 plus 9 and you turn it around to 9 plus 1 plus 4, you get 10 plus 5 plus 13. Like it is not working. Next one would be 16. 16 plus 9 plus 4 plus 1. 17 plus 13 plus 13 plus 17. Like that trick isn't going to work now. So no, there's not a kind of a simple. And again, I wonder historically how much of a rabbit hole was that? How did somebody figure that out? I actually don't know the answer to that. I'll show you a cool way I'm going to figure it out. You can steal it from the book, but where did it come from? And of course, this just gets worse. If we had a cubed equation, then we'd have cubes, 1 cubed plus 2 cubed plus 3 cubed to add up. And so the fact that there's formulas sitting in your book for k is 1 and k squared and k cubed, the fact that there's formulas for those and that somebody figured them out is pretty darn remarkable.
Is there a way to do it for, I guess, kind of series of arbitrary powers, or is it like we have to find a new one for every single, squared and cubed?
Yeah, great question. Because the formulas in the book are different, the answer is they're all different. Now, maybe there's a pattern to the patterns. In other words, if you figure out the first three, this is what deductive logic is. Is that right? Deductive, inductive, I can remember which one's which. Is like, hey, I think I see a pattern to the patterns. So maybe I have to find the first 3 or 4 manually, but then I say, oh, I see what's happening. All I have to do is increase the power and add another n plus 1 term, or first it was n plus 1, now it's n plus 2, and then it's n plus 3. Maybe there's some kind of a pattern to the patterns, and that's what drives mathematicians crazy, or makes their life awesome, whatever, however you want to look at it. It's trying to come up with that kind of stuff.
Thank you. See you tomorrow.
See you tomorrow. Neat stuff. Let's see. I should stop recording.